everyone wants to be an hacker, right? That's the reason why I'm sharing my talk Exploit Development for Dummies with you guys. This talk was initially created for Barracuda's EMEA Tech Conference in Alpbach, and I will give this talk live tomorrow there. However, I want to share it with you guys over the internet. So what is it all about? It is all about exploits. So how are these random hex character strings created in the first place? How can you find vulnerabilities in software products? And how can they be abused or weaponized to finally overtake a target system? Whenever I was thinking about the typical exploit developer, I had a picture like this in my mind. So a nerdy guy sitting alone in a dark room doing his hex character stuff, but that's simply not true. By now I know several people who do exploit development for a living, and not a single one looks similar to this guy here. So it's just Hollywood. I want to introduce myself briefly because I think it's important to know that, who am I? So my name is Florian, and I'm an IT security expert. I do IT security and only IT security for a living, and I started my own company, BIT Security, only 2 months ago. What I learned over the last years was that penetration testing is quite important, but most companies simply can't cope with the results. So I was doing penetration tests, I created a really cool report, I presented my findings in front of the top level management, and 2 years later I found the exact same issues in the same infrastructure. What that means is, I think we as a penetration testing industry, we have to change the way we communicate. And that's exactly what I'm doing with BIT Security. I'm helping my customers over the long run to increase the security level. As I don't talk about who my clients are, I have other reference. And in my case, it's all of bug bounty hunting stuff. So I reported vulnerabilities to Google, to Barracuda, to Checkpoint, to Intel. So many well-known vendors, and I focused myself on binary exploitation. And this is exactly what we're going to cover in this talk. However, first I want to discuss a topic that's very important to me, and that's information sharing. So more and more presenters or companies try to keep their information to themselves. And so you're seeing this picture taking is prohibited signs everywhere. And I think that's the wrong way. We as an information security community have to share our stuff. So I'm happy if you're sharing my slides, if you're taking pictures, just share it. The first question whenever I was thinking about exploits is, who the hell is creating these exploits in the first place? And I think I have here the 4 most important groups. On the one hand, the groups that are creating the most valuable exploits, and on the other hand, the group that is creating the most exploits that are out there. So the first one is nation-state actors or advanced persistent threat groups. So this is where the money is. For example, last year the NSA lost a part of the cyber arsenal, and one was especially interesting, and that was the Eternal Blue exploit that has been leaked in there. The Eternal Blue exploit is a so-called remote code execution vulnerability in the Windows SMB stack that boils down to simply overtaking a Windows server by just looking at it. So it's one of the most dangerous vulnerabilities out there that was exploited in this tech code. And it really shows us how advanced some of these threat actors are. And I guess if the NSA has such capabilities, Russia has the same, for example. Then there's another group. It's the group that is doing exploit research just for the sake of money. So there are companies out there like Zerodium, and they are buying high-value exploits from independent security researchers. For example, they are paying up to $1.5 million for remote code execution vulnerabilities in the iOS software stack. So there is a really huge money in there. Now move on to the, largest group. That's just people doing exploit development for fun. So they are most likely targeting obscure or old or unused software products and trying to exploit them. And the reason for that is that they simply want to learn the most likely basics about exploit development. So the largest group just doing it for the sake of learning. And then there's the group that's most important to me because I'm a part of them, advanced penetration testing and red teaming attacks. So whenever a client is quite advanced in the IT infrastructure services or they are, for example, a software developer themselves, they may have the need to really check applications in depth. This is what I really love to doing because, yeah, it's interesting. So you're checking the security of a single application, or you're trying to break into a really well-secured network by abusing a new technique or a new vulnerability that you have discovered. And this is exactly what we will discuss next, because I think the story is the most important part of a talk. So we need to come up with a story that we can build our talk up on. So, ladies and gentlemen, may I introduce you to Douchebags Inc. The name sounds maybe a little funny, but that's intended. And you can also guess what they're doing. So they are a high-quality bag manufacturer, and they produce the best bags in the world. So they have the top-level quality, and no one else is even near them. And so they have a problem. There is a competitor far, far away that might tries to break into their network and steal their production secrets. So yeah, there are several signs that they are already trying to do so. So Douchebags Inc. Ordered our services or called us for help, and we should try to break into the network and should try to find as many vulnerabilities as possible. As I had tried to break into the network several times already, I know that they have done or have created a quite secure environment, and we have to come up with a plan that's a little different from what I would normally do. So here's the plan I'm going to focus on the next few minutes. It's a simple 4-step plan, but let's try to take a closer look at what these bullets really are. So the first one is the classical start of a penetration or red teaming attack. It's just information gathering. However, I know Douchebag Inc.'s network or security level is quite good, so we have to come up with a different attack plan. And my attack plan is binary exploitation, so we have to identify a target that we can abuse. What I mean here is we have to find publicly accessible information that tells us about the applications they are using. Maybe we are able to find, I don't know, an image viewer they are using or an ERP system that they are using. Maybe we find a reference on one of their vendors that they are using where they tell us exactly what they have bought. So just looking at publicly accessible information to find out if there is something interesting that we may can abuse in the further steps. Then, when we find something interesting, we have to check its security level. So we have to check if there are vulnerabilities within the software product that we have identified as an interesting possible target. We will do something called fuzzing here. As soon as we find something, we then have to weaponize it. So we have to place our malicious shellcode in there to, for example, infect the target PC with our malware. And finally, well, we have to carry out the attack. And if everything works out well, we can win or we can gain access to the internal network and thereby prove that there are some issues that should be should be solved because an attacker could abuse them to gain access to something they hadn't had before, and that's not good. So let's start here with the information gathering and target identification phase. That's the only part I'm doing in PowerPoint because it would take too long otherwise. So how do you do your reconnaissance? Well, the first part is always just use Google. You go on google.com and you put in there Douchebags Inc. and you find a lot of valuable information. Like, for example, well, you find out that they have a homepage. That was pretty clear, right? However, there's a really super secret hidden feature on Google that almost nobody uses, and the reason for that is Google is too good. No one is looking at pages 2, 3, 4, 5, up to 10. But I do so. I really love to take a look at page 8 and 9 because they're the most obscure things and sometimes they are really, really valuable from an attacker's point of view. So I think on page 5 I found this one here. Can you spot the interesting one? So here it is. It tells us that Douchebag Inc. is using Google Groups. So they're using the G Suite. And I guess they have an issue here because it looks like their internal IT discussion mailing list is publicly accessible. That could be interesting. So let's take a look here. And yes, we can gain access to their internal stuff. And let's scan through the threads that we're having here. There's a kids yard sale, but well, we don't care about that. Someone is unable to use their VPN. Word crashes. Well, that happens to me all the time. But this could be interesting. Earth and View image view for DXF files. So maybe that could be interesting. Does anyone know OpenView? Well, OpenView is the first application I've installed, I guess, because yeah, it's available, or you can download it since, I don't know, the 17th century. So it's supported for more than 20 years, I guess. It's developed by an Austrian guy called Irfan. And it's a super simple, super fast image viewer. It's a little bit obscure, but it still has more than 1 million downloads per month. So quite an interesting target for us. So let's take a look at this thread in more detail. There is Sarah, who writes to the internal IT discussion list if they can install the DXF plugin for OpenView. The reason for that is that she has to scan through 10 to 20 files, CAD files in this case, at once, and that takes quite long to load within AutoCAD. Yeah, well, that's true. So what is Mark replying here? Well, yeah, he checked that, and yeah, they can install the DXF plugin. They will do so in the evening, and that's the really interesting part here. They are using OpenView 4.5 32-bit on all clients. And that's the best possible gift we can find on the internet, because now we know exactly what application they're using, what version they are using, and that they have the 32-bit version installed. So perfect. This will be our target, at least if it fulfills our requirements, because this talk is called Exploit Development for Dummies, so we can't cover all the interesting or complex stuff, like, for example, a use of the free vulnerability on the heap. No, we have to focus on the basics. And one of the most easy to understand in an IT security sense exploits is a so-called buffer overflow or stack overflow. It's still pretty complex, don't get me wrong, but it's the easiest way to exploit something here. And I want to give you an overview about what a stack overflow is. So here it is. We have a really simple application. So the most easiest application, or the simplest application I can think of, is just the main. The main function is a little bit special because it's executed as soon as you double-click the exe file on your desktop. In here we have no logic. Still, there is a special memory region called the stack. And the stack is created by the operating system for us, and it contains the application state, or it records the current application state. And there is a little bit, a strange thing about the stack, because it's growing in the wrong direction. So it grows from the larger addresses to the lower addresses, from, for example, 100 to 10. So it grows in the wrong direction, as I told you. Every single function that's executed gets its own so-called stack frame. The stack frame contains, amongst others, the parameters that are received by a function, the so-called return address, and possible local variables that are used within the function. So let's move a little further, and let's add a little bit of code here. So now we're talking about an image viewer, a really simple one, but still. So there's the main function, and the main function receives one parameter, and that's the input file, I guess the file that should be displayed on screen. And as you can see, it's calling the load file function, and that's the function that has been added below here. And yeah, as soon as the load file function is called, well, there's a stack frame for the load file function located or created on the stack. Everything works out pretty well here. And let's take a look what this load file function is doing here. Well, it also receives the file that should be loaded from disk, or that should be prepared for displaying. Then it has a temp buffer variable with a fixed size of 10 bytes, and then it's trying to load something from disk. Well, can you spot the issue here? We have a fixed size buffer with 10 bytes, and we're loading data from disk without any error checking. And this could lead to an issue, because if the input file has more than 10 bytes, well, what's happening then? Well, I can tell you. We are creating a so-called stack overflow. Because what's happening here, we have a local variable, the temp buffer, and local variables grow in the right direction, so from lower to larger addresses. But as you can see on the left side of this slide here, we now are able to overwrite the return address. So an attacker who abuses this issue we have seen here on the right side and overwrites or writes beyond the 10 bytes that have been allocated on the stack is able to place arbitrary values at the return address. So by doing so, we can gain arbitrary code execution. This is true because as soon as the return function is executed, the CPU loads the address that is stored within the return address field on the stack and continues execution from there. What that means is an attacker who is able to overwrite the return address is able to resume or redirect the execution flow to an address of his choosing. This basically boils down to we can execute whatever we want and thereby infect your PC. Does it make sense? If not, you can place comments down here. But let's move on in the meantime. We have identified Overflow as an interesting target, but now we have to check if it fulfills our requirements. Because again, this talk is called Exploit Development for Dummies, we have to check if the application is not using, for example, DEP and the ASLR. So let's move on. I've got two VMs here. And this is the first one that's interesting for us. And on this debug machine, I've got Overflow installed. Let's start it up. And now let's use Process Hacker to check out if this application is well suited for our attack. So we have Overflow running down here, and we want to check if it's using ASLR and DEP. So to do that, I've launched Process Explorer, and using the Choose Columns customization menu, I've enabled the ASLR and DEP columns. So in here, I can now check that Overflow is not using ASLR and it's not using DEP. Well, that's fine, but I guess I should explain what these are, right? So what's ASLR? We are taking a look here at the inner workings of Overflow. We are checking what modules have been loaded. So there is not a single application that's self-contained. Every single application that we are using needs the operating system to fulfill tasks, like for example, drawing its windows. And to do so, it's loading additional DLLs, as we can see here. So amongst others, there's the oldest 32 DLL, there is the kernel 32 DLL, and so forth. And every single DLL is mapped at the so-called base address. That's the address where the DLL basically starts within the memory or within the process memory. And all the functions that are provided from within these DLLs can now be called with base address plus function offset. And this is well defined and is fully automated from a developer's point of view. From an attacker's point of view, this is also very important, because if you know the base address, you can also call arbitrary functions from within kernel 32 or any other DLL. And that's important because also attackers depend on the operating system. For example, they may want to spawn an external process, or they may want to add a new user to the system. So what ASLR is doing, so the address space layer randomization is, it's randomizing these base addresses here. So whenever you reboot the system, all the DLLs get a new base address. That means an attacker can't simply hard code the addresses of the functions he wants to call, and that makes exploitation a lot harder. So whenever possible, use ASLR, because again, it makes exploitation a lot harder. Then there's something else. It's called DEP, the Data Execution Prevention. And to take a closer look at this here, we will switch over to Immunity Debugger. Immunity Debugger is a debugger that we will use later on in more detail. But for now, it's enough to attach to the Overflow process. So here it is. And take a look at the memory map. So here again, we can see what memory or what functions or what parts are mapped within the process memory. So for example, if Overflow is opening a file for displaying, it also maps the file here. So it's a memory mapped file. And we can see, and that's the interesting part from a DEP's point of view, there's these access bits. So an access column where we have three different letters. It's R, W, and E. R stands for read, W stands for write, and E stands for execute. So what DEP does is it hinders the execution on memory locations that shouldn't be executable. Back to our image viewer example. So, for example, our image viewer is vulnerable. An issue is abused while the image file is being processed for displaying, and the attacker tries to execute code that has been delivered from within the image to finally overtake the server that we're on or the client that we're on. So if the image view is using DEP, this will not work out because the memory mapped file will not be marked as executable. So the CPU will not execute a single instruction from these memory locations, and otherwise will terminate the process. So really, really interesting and a really, really powerful feature to again make exploitation a lot harder. But as I told you before, OverfloW is not using ASLR and it's not using DEP, so it's the perfect target for our scenario here. Let's go back to our PowerPoint. Because we have cleared the first part. We have identified OverfloW using this publicly accessible internal mailing list. We found out that it's the perfect target from an attacker's point of view because it's not using all the modern mitigation strategies that Windows has provided for, I guess, every version since Windows Vista. So, well, move on and let's try to identify targets within the OverfloW application. The big question is how to do that. Well, there are multiple ways. Amongst others, you could do manual analysis, but the one I prefer more is so-called fuzzing. And what's fuzzing? To understand that, we first take a look at how a normal process execution looks like. So whenever you receive an image file and want to take a look, you just simply double-click the image file. The operating system looks up who's responsible for handling, for example, JPEG files, then spawns OverfloW. OverfloW processes the image file and finally displays it. So now we want to find out if we can abuse something within OverfloW to run our malware. And to do that, we again use the fuzzer. What's the fuzzer? Well, a fuzzer is a thing that we place on top of this execution file we have seen here. So the first thing is the fuzzer starts with not a single image file, but with a so-called seed file folder or input. There are simply more than one image file within the seed files folder. Every single seed file is then changed depending on the so-called fuzzing strategy. So for example, the fuzzer flips random bits or bytes, it truncates the file, or it adds random padding in there. That's important because next we're starting the OverfloW process and we are closely monitoring the processing of the image file that we have modified in the first place. So some things will work out just fine from OverfloW's perspective. So maybe we have created an image that's just garbage or it's black and white or whatever. But some things may trigger undefined behavior within the parser and finally lead to a vulnerability or just an error. And that's the interesting part for us. We are repeating this process hundreds or even thousands of times. So we're changing the input files and we're closely monitoring what's going on. And thereby we find out that, or we're trying to find out if there is something we could weaponize in the later end. So that's enough from the theoretical point of view. Let's take a closer look at how this really looks like and what you have to do to fuzz your own applications. And we will do fuzzing with the so-called BFF, the basic fuzzing framework from the US CERT. BFF is working on pretty much all operating systems that are out there and is free to download. You just have to Google BFF and US CERT, for example, and then download it from the first Google hit. It's available for Windows, Linux, and macOS. And if you install it on Windows, it's best to use Windows XP because there it's able to capture the most data and it's able to give you the most valuable automatic analysis. So, what is BFF? I've installed it on this machine in its default location, cBFF, and as you can see here, it's a Python script. It's not a simple one, it's a pretty large one, but it automates the whole fuzzing process. To do so, you have to set up a so-called campaign with this configuration file here, and it's just a simple plain text file. So every single campaign you set up has a so-called ID, so it's just identifier. And then you have two really cool special features that I want to highlight. The first one is keep hidden bugs. Because there is something really special about fuzzing. Sometimes you're changing the input files, you're launching the process, something goes wrong and the process crashes. Then you retry it and it works fine. So that's not really usable from an attacker's point of view because you don't really know what's going on here. Is your exploit working or is it not reliable working? So you can't use these kind of issues and hence you just ignore them. And an issue that's not clear, or that is not always exploitable, or is not always does not always trigger crash, is called a Heisenbug. So we ignore those, yeah. And then there's the button clicker, because some applications bring up error messages when they fail to parse the input data. And what the fuzzer is doing, he starts the application and checks if it's crashing. If it's not crashing because it's bringing up an error, we have to wait for a timeout. So sometimes you can just click on the OK button within the error message and the application closes down by itself, and that greatly speeds up the fuzzing process. But that's not working within Overflow. Next, we have to set up the real target or fuzzing configuration. So we define which application we want to fuzz. In our case, it's the iFU32.exe application. And our command line looks as follows. We have first the exe application, okay, fine. And then we simply put in the seed file. So the file that the fuzzer randomly changed. And all the seed files are placed within this directory here. So just to give you insight on that one too, browse over to seed files and Overflow. And the more seed files you have, the better. So in my case, I have, I guess, about 50 seed files, yes. They should be pretty small. They should be just self-contained. And the more obscure, the better. Because I'm pretty sure the code for parsing, for example, BMP files is pretty well tested, and 100 people have already tried to fuzz it. The big question is, has anyone cared about fuzzing BPM files or PGM files or, I don't know, an XPM file? I don't even know what it is. Additionally, the more obscure the file, the better. So, for example, Overflow is also able to extract the icon file from DLLs and exe files. So I'll place these in here too. So the fuzzer simply opens one file after the other here, replaces stuff, adds stuff, depending on what you set up in the config file, and then it checks what Overflow is doing. I told you about the fuzzing strategy before. So the BFF fuzzer contains several different fuzzing strategies. The one I use most often is the byte mod, and it simply replaces bytes with random values. So yeah, pretty easy. So that's everything you have to know from a configuration point of view. No, I don't want to install any updates right now, so I'll try tomorrow. No, go away. So let's try the fuzzer, right? So we're just moving over to BFF, and then we start the Python script. So the first thing that's happening is it verifies the configuration, so it launches the Overview process once with one of the input files. Then it gives us a few seconds to verify that everything has been working, and now the real fuzzing has been started. So as you can see, Overview started over and over and over again. And because the fuzzer is randomly changing bytes within the input data, you can see that some input files simply can't be filled. So there are error messages that show up. There is broken data being shown, as you can see right now. And additionally, we have to our log over here. And whenever there is a crash, the BFF fuzzer does something really interesting because it does so-called minimization. That's what we see here right now. So whenever there's a crash, we have to find out what caused the crash. The reason for that is the fuzzer is not only changing a single byte, but multiple bytes at once. So with the minimization process, it tries to find out what byte really caused the crash in the first place, and additionally, it tries to find out if there is more than one change required to really trigger this issue here. Whenever a crash is identified, there's also a pre-categorization taking place. So the fuzzer tries to figure out if this crash could be exploitable in the end. So let's take a look at what we get as a result from BFF's fuzzing process. And yeah, so there's the results folder, there's our campaign, and there's the crashes folder. As you can see, here's the pre-categorization. So we can see issues that are marked as unknown, probably exploitable, and exploitable. And yeah, within here we can find a large number of unique crashes. And to find out if a crash is unique, the fuzzer internally is using these random, or these numbers here. They are not random, they identify the crash location, but for us they are just random. When we look in here, we can see that we have the file that caused the crash, we have the minimized file, so the one where the fuzzer tried to find out which change really caused the issue. And then we have the drill down files, or the drill results file, I guess that's this one here, where you can find out a lot about what has happened. You can find out that there has been 1, 2, 3 crashes in this case, so 3 exceptions that are interesting for us. You can find out that the first one is about a read access violation on block move. Here we have a tainted data control branch selection issue. You don't have to care about what these are in detail, because there's one number that's the most important for us, because the BFF fuzzer uses the bang exploitable WinDBG extension to create a so-called exploitability rank. This number here goes from 0 to 100. 100 means you can ignore this bug from an attacker's point of view because it's not exploitable. 0 means, well, that's a goal. That's really interesting for us. So 45 could be exploitable, but would take a lot of time to really find out if it's reliable, exploitable, and how. So to gain a little bit more insight about what we have found already, we can use the drill down script. So that's the drill results. Results.txt. Start results, there it is. And what that does, it passes through all the drill down results and creates a sorted list based on the exploitability score. As you can see, there's a crash with an exploitability rank of 10. That's really interesting. So let's take a look at the crashes we are having here. So exception 0, tainted data control branch selection. We don't care about that one. We don't care about that one either, but that one is really interesting. A read access violation on instruction pointer. So a read AV on AP. Makes sense, right? So what that means is we most likely were able to trigger a stack overflow and overrode the return address with this value here. So because there is no valid code at this memory region or this memory location, the CPU crashes or stops the process. So that's pretty interesting by now. However, there's something even more interesting. The memory address where we are trying to execute code from has been found within the fuzz file. So if we are really lucky, we may be able to simply change a few bytes within the input data file to redirect the execution flow to a memory address of our choosing. So let's summarize what we have found till now. Well, our plan, we have found OrphanView, we have been using the BFF fuzzer to find vulnerabilities within OrphanView, and well, we have found one with an exploitability rank of 10. That means pretty interesting and looks like a stack overflow. So let's try to weaponize that one. To do that, we'll just do a quick recap what we have already discussed on the stack overflow. So the attacker is able to overwrite the return address. That's exactly what the fuzzer has found here, and is thereby able to control the execution flow. What I have in mind now is that we are overwriting the return address, redirect the execution to within our or to code within our image, but not to the part within the real image content, but we just prepend or append or just overwrite it with our shellcode. So we overwrite the return address with an address that points to our shellcode, and our shellcode is generated within the Metasploit framework because we don't have to write that by hand. So all these random hex characters we see in these exploits most likely are created using a framework like Metasploit framework. You just have to write the first few bytes or the last few bytes or so by hand, but most likely they're created as some kind of framework. But that's the plan. Again, we will analyze the crash that BFF found in more detail. We will try to overwrite the return address with a pointer pointing to our image file. And because we have placed a shellcode in there, we can now execute arbitrary code. Does that make sense? Okay. If not, again, you can use the comments down here to paste the questions. Let's try to weaponize that one. So switch over to our exploit machine. That's the Windows 7 we have seen before already. And we now have to take a closer look at OrphanView. Yes, we have to take a closer look at OrphanView, but again, where is it? The CPU window. We also have to discuss how Immunity Debugger is working, because we will now live within Immunity Debugger. There's nothing else than bytes and random hex characters from now on. So let's open the OpenView32 process and let's take a closer look at what we're seeing here. So this is a debugger. Immunity Debugger is a debugger, and it allows us to view what an application is doing in the background. And it's split up into 4 sections. So let's discuss one section after the other. The first one on the top left is called the disassembly. So what we see here is the content, or no, it's the disassembled application code. So we're seeing that the application is calling the moth, the sub, the push, whatever as Intel assembly instruction to do whatever it's doing. We can step through all these commands here. So these are not written by the programmer, but created based on the program code that has been written by the compiler. So as you can see here, by pressing F7, for example, we can execute one instruction after the other. And that's really powerful because thereby we can learn what the application is doing in the background. We can also, for example, set up breakpoints. So with F2, we can highlight this line in cyan, I think it's called, and by pressing F9, we can execute until we hit this breakpoint here. Pretty powerful and allows us to understand what the application is doing. However, to really understand what we see here, we also have to take a look at the thing on the right here. That's the registers view. So here we see the contents of EAX, ECX, and so forth. So these are general purpose registers that they used during the execution of the application to keep track of what it's doing. So maybe we see numbers here, we see strings here, and there is something really special. That's the EIP, that's the extended instruction pointer. That's the register that holds the instruction, that holds the memory address of the next instruction that we're going to execute. Exactly this one is overwritten during a stack overflow. So if everything works out with our exploit or the data we have been provided by the fuzzer, we can place arbitrary values in here. We already talked about the one on the bottom right because that's our stack view. Here we can see what's on the stack. We can take a closer look, for example, on where we return to. If there is a structured exception handling chain, so is someone catching errors that occur? Yeah, very powerful and very valuable information. On the left side, we have our dump, so we can just take a look at every single memory address that the application is using, and we're just seeing bytes here. We could switch the view, but bytes are fine for our case here. Whenever we're starting the debugging process here, we are automatically stopped at the program entry point. So this is doing the debugger by default, and we can then continue the execution and just use OpenView. However, we are not really caring about OpenView in the first place. We just want to analyze if we're able to override the instruction pointer. And so we will be covering our fuzzing result here. So that's exactly what we have created or found on the Windows XP machine, and that's the file that's crashing Overflow there. So we copied it over to this working set folder because this is the folder I will use for the later demonstration. So Overflow is really cool because it doesn't really care about the file extension. So the first thing we'll do here is we'll start the CMD. We'll move over to this folder here, and we'll rename this large folder file name to just file.jpg. Because Overview doesn't really care about the file extension, but the operating system does. The operating system now thinks it's a JPEG file. We can double click it, and Overview is spawned to finally display this image here. And Overview checks, well, that's not a JPEG file, but an exe file, and it's trying to extract the icons here. So that looks interesting by now. Let's take a close look at this process using the debugger. So using the argument setting here, we will just put the file.jpg as the first parameter on the command line, restart the execution, continue the execution from the program entry point, and take a close look at what's happening here. As you can see, something has happened, an access violation when executing 3C, 0A, and so forth. What that means is, as you can see here, the extended instruction pointer has been overwritten, most likely by a buffer overflow, and allows us to, or tries to execute code from a non-invalid address or an invalid memory region here. That's interesting. Let's take a close look at the drill down file we have received from the fuzzer, because there was something even more interesting. Byte pattern is in fast file. What that means is the value we have in EIP, so 3C and so forth, is located or can be found within the input file, so the file.jpg file. So maybe if we are lucky, we can just change these values within the input file and thereby are able to fully control the instruction pointer. So let's try to do that. We are launching my favorite hex editor here. It's HXD. And we open our image file here. So desktop, large folder or random folder name, workset, file.jpg. So in here we simply go to find hex values and we're searching for 3C, 0A, 0D, 3. And we don't have a single hit. Well, that's interesting, but it's easily explainable because we have to take the endiness into account. So we have to search for 3E, 0D, 0A, 4C. So we have to change the location of the bytes. And then we are able to find these memory patterns or this memory pattern within the file. So let's try to change it here. Restart the application and observe what's happening. Well, we're still crashing on 3C, although we have changed it to 4C in the file. So either it's not working or we have more than one hit for this byte pattern here. And yes, there is more than one hit, so change that to 5C. Let's retry that here. Continue from the program entry point, we don't care about it. So we are still crashing on 3C. So maybe have another hit here. Yes, and let's overwrite that with 6C. Continue from program entry point. And now it's getting interesting because we have now overwritten the extended instruction pointer with 6C instead of 3C. So our change from within the hex editor directly reflected to the current execution state. So let's try to overwrite that with ACE and again restart the application here. As you can see, the instruction pointer has been overwritten with ACE. And that's really cool because now we can fully control the instruction we want to execute next. Well, we can't place an instruction here, but we can point arbitrary values in here. It means we can define the next instruction we want to execute. The big question is, what instruction do we want to execute next? And the answer is pretty simple. We want to execute a custom one. So some instruction that we will place later on into our work file, into our malicious JPEG file that we have here. So let's try if we can find one byte or the random byte patterns from within the input file within the process memory of OpenView. So to rephrase this question here, has OpenView loaded the whole file into memory? And we can use view memory and search to search the full memory of the current process. So there's one hit, another hit, another one, okay, so we have, I guess, the full file mapped 3 times to memory. And now we have to check if we find a reference to these memory locations. So we have it mapped on 0144, we have it mapped on 00D, and we have it mapped on 0011. So let's take a look, beginning from the stack here. So we have 000 on the stack, we don't care about this one, we have 000 here on the stack, and then we have 0145. So that could be interesting because that points to within these memory locations here. So I guess the third entry from the stack points to data that it's been loaded from our file here. So let's take a closer look. We just click here and click on following up, and we now see on the left side the destination of the pointer. We're from the stack, and we just go here and click on breakpoint. Binary copy. We move over to XHD, and we can find the exact same pattern where this pointer is pointing to within the fast file. So what happens if we replace the first 2 bytes with CC, that's a breakpoint, we will use that later on, and restart the application flow. So program it, entry point, we don't care about that one. We're still crashing on AAAA. We again have here the third value on the stack that looks interesting, and if we click here follow dump, we can see that we're now pointing to CCCC. What that means here is that we can now place our shellcode in here. So we can, or at least we can in a few minutes, execute random or arbitrary commands, because this data here is mapped on the stack or within the memory location, within the memory of the Overflow process. There is only one part missing, because we have to override the instruction pointer here with a valid address that allows us to get to these C's here. The big question is how to do that. Well, let's try to find a sequence of instructions that could allow us to do so. What do we have to do to get our code execution here? So we have our stack here, and what we need to do is we have to remove the first line of zeros, we have to remove the second line of zeros, and finally we have to call the instructions that are stored at this memory location. And there are assembly instructions to do so. That one is a pop. A pop removes the first line here and stores it somewhere else. We don't care about it. Then we need another pop that removes the second line of zeros. And then we need a return instruction, because a return instruction takes the next value from the stack and continues the execution there. Luckily, we don't have to find these instructions by hand. No, there is a plugin to do so. There is mona.py. It has been written by the Golang team, and it's a really cool Python script. It's a plugin for Immunity Debugger that allows us to automate many of the most boring tasks within exploit development. So for example, I can now go down here into our command line and type mona, bang mona, structured exception handling, because these series of instruction, pop, pop, red, are normally used within so-called SEH, so structured exception handler exploits, but still we needed two, although we are doing a normal buffer overflow. As you can see here, the Mono plugin found more than 1,100 pointers that are interesting, but let's start with the first one. So at memory address 004D0BA9, there is an instruction sequence of pop EBX, pop EAX, red. So we remove the first line of zeros, we remove the second line of zeros, and then we call the third, or we execute starting from the memory address where the third element from the stack is pointing to. So basically our CCs. I really like that one. So let's copy that address here. So it's A9, because we have to take the endiness into account. A9 0B 4D, excuse me, B 4D00. Let's copy that and go back to our hex editor. We have to search for our There it is. And we can now overwrite it with the address that we have identified. So it's the pop-up ret. When we restart the OverFlow process here, I expect the following to happen. OverFlow opens the image file, parses the content, the stack overflow happens. Instead of the A's here, we will place the memory address 004D0B A9 here, which executes a pop, another pop, and a ret, which basically boils down to I expect Immunity Debugger to hold at our CC breakpoint here. Let's try it. Immunity Debugger breaks at the program entry point. We don't care, so we press F9. And perfect. We are stopping at an int3 command. And that's CC, the shellcode we have placed in memory. Well, right now it's on the shellcode, it's just CCs, but still quite interesting by now. So just give me a second, because I have to close the execution here and have to just restore my backup file, because just to ensure that everything's working, I've created a nice backup here. Let's close that file, I'll reopen it. What I did here is, namely, I've prepared everything so that when we execute that file here, oh, I've renamed it wrong. Shouldn't do that. Close. There it is. It again holds at my CC comments, but I've placed a lot of A's in here, so that's also here. Come on, my friend. Oh, yeah, here it is. So many A's. The question is, where do we get our shellcode from? And I've already told you we will be using the Metasploit framework for automatic shellcode creation. For that reason, I've got my PuTTY window here, and PuTTY has been connected to a Kali installation. And for that Kali, I've already prepared the commands I want to use. Okay, hotkeys don't work. Desktop to do, here it is. So paste that one. What we're doing here is we're calling MSFVNow. That's one of the command line tools from the Metasploit framework. We are using the Windows exec payload, and we tell this payload here to execute the calc command. Finally, for execution, we use the structured exception handling. So hopefully, OverFlow is catching our issue here, or the problem we have caught or caused, and brings up a nice error message. To get the shellcode out of the file, so the calc.shellcode file, we can again use Linux built-ins. So we're using XXD here. And here's our shellcode. So pretty easy to generate shellcode, and just copy it. And then we click binary paste, and our shellcode has been placed in here. So the first one is FC, and then on the end we have 00. Let's verify that. 00 on the end, FC at the beginning. So it looks good. And now, finally, retry that within the debugger. Okay, interesting. So we've restarted the application. It has been halted at the program entry point. We press F9 so that the execution continues. Our breakpoint is hit quite in front of the shellcode we have pasted. So you can see here, FC, it's the beginning of our shellcode. And by pressing F9, our shellcode is executed and the calculator is spawned. Really cool. So let's try that in real life here. So let's double click the file. So what has happened here? We've double clicked the file, we've verified that everything's working. Immunity Debugger showed us that calc has been spawned, but if we double click the file, it doesn't work. Well, again, easy to explain. There's this CC here, and that means breakpoint. However, if no one is watching for or is catching the breakpoint, the application will be terminated. So we have to replace that one with an up. And now let's retry that. We just opened the image file here, so a JPEG file. And because we are using a Stack Overflow, and that's really, really cool, calculator is spawned. So that's really a zero-day vulnerability. No one has ever seen this before. Well, the people at the Barracuda conference have so, because I will be giving this talk before I will post it on the internet. But still, almost nobody else has seen it before. And it's pretty cool because we now can simply abuse an image file to execute arbitrary code. So just to summarize what we have been able to do, we have used publicly accessible information to find Overflow. We verified that it's not using DEP and ASLR. We have used the BFF fuzzer to find interesting crashes. Because of an exploitability score of 10, we took a closer look at one crash and found out, well, it can be abused because by now, simply opening the JPEG file launches the calculator. So we can create an attack based on that. So let's create an attack that's interesting from an attacker's point of view and then move over to the victim's point of view to check out how we can really abuse that in a full attack scenario. So again, back to our Windows 7. And I want to introduce you to another tool that I've built. It's called the B shell. So the B shell is a simple PowerShell red that I use during my social engineering attacks and sometimes during my red teaming attacks. And as you can see here, you can set up different campaigns. That's just my dev machine, so there's just that. There's multiple systems that can be controlled within from one campaign. And here's one of my development machines, and you can see it's just a PowerShell web interface. So what I want to do is I want to drop my PowerShell client using the image file we have created. So there's a nice feature within my B shell. You can just create a one-click launcher. It's a PowerShell command that infects the PC with my PowerShell red. And we now have to wrap that again in a valid shellcode. So here it is. And again, on our Kali Linux, we use Metasploit with the exec plugin to execute my PowerShell dropper, as you can see here. So PowerShell is used to download malicious code from my command and control server on the internet, which basically connects back and then allows me to remotely control the infected PC. So here's the shellcode. Let's use that shellcode and drop it in here. So as you can see, our shellcode has been pasted. We can even see the PowerShell command that's being run. And so there's only one thing missing. How can we deliver that image file to our victim? So let's close everything up here and change the point of view to the view of our victim. Let's say we had a nice lunch and suddenly we receive an email from James Smith. You have to know that James and Smith are the most used names in the US, so you can help yourself with statistics here from, again, the attacker's point of view. And James Smith is inviting Sebastian Wolfs, who works at Douchebags Inc, for a beer. Hi Sebastian, we haven't talked in a long time. I would like to chat with you again over a beer. Do you have time next Friday? And in the meantime, here's a funny cat image, because everyone loves cats, right? So just double click the cat.jpg file. Earthling view reports, well, can't decode, doesn't contain any icons. Okay, something went wrong during the transmission of these files here. You may have seen those PowerShell windows briefly. They were used to infect the PC. So if you take a look at my command and control interface here, you can now see that there is a second client online. So it's the exploiter PC because it's just my test machine here. And if I click on that machine, if I activate it, we can fully control it. So for example, we can use that one to take a screenshot. We can run any kind of PowerShell malware. We could take a video, we can install a keylogger. We also can spawn arbitrary processes, like for example, if I place in Notepad here, well, it's executed and you can see Notepad is spawned. So it allows me to take full control over the affected PC. And the only thing that was necessary to do so was a malicious image file has been opened. So I guess that's a really, really cool issue. We have discussed what is necessary to really overtake a system. I just want to again recap. We have identified what the issue is. We have found an abusable vulnerability using the BFF browser. We have weaponized it. We have been able to launch Calculator. And for the final attack, we deployed the B shell rat on the client PC. And the only thing that's necessary from the victim is they open an image file. So, ladies and gentlemen, I guess we have been able to successfully win this one. And I guess that's the wrong icon for that here. I really love beer because you have seen Sebastian has been invited for a beer, so I will go for a beer too. Thanks for watching. Oh, well, there is one thing. I told you that's it has been a so-called zero-day vulnerability, so no one knew about that issue. As I'm always doing responsible disclosure, I've reported that issue to Irfan, and Irfan is very fast in replying. He's really interested in keeping OrphanView safe, and he immediately started to analyze what's going on, and he found out, okay, interesting, and he found out that's not really OrphanView here that has an issue, but he's just using an old Windows API. So in the end, we found out that the issue we have exploited here wasn't caused by OrphanView by itself, but by the Windows API. So it was more or less a Microsoft bug that we have used to overtake the system here. Anyway, Irfan by now released a new version. That's the 4.5.1. That fixes the parsing issue in a way that it's using new APIs, and thereby, everything's fine. So my conclusion is, you can now again safely open image files that have been sent by me. Thanks for watching, and if you have any question, well, just use the comment form below. Bye.